Good morning. Let's continue on the line equation in 3 space, and we'll look at a few examples today. If we finish early, we'll get on to another topic called parametric equations for curves in 3 space. So let's do a quick review on line equations right here. Okay, so here is basically what we have done in the previous lecture. We derived a general equation for lines in 3D space. So in general, essentially, if you are given a point the line goes through and a vector the line's parallel to, okay, so there are 2 informations basically you're looking for to create a line equation: a point the line goes through and a vector that the line that is parallel to. Then the line equation is so specifically, maybe I should put down the information for the point. For example, let's say for the point I'll call it P naught. Okay, so this is a specific point the line goes through, and the vector I'll call it the parallel vector V at here. Okay. So V1, V2, V3 are the components of the parallel vector. Then this line equation is x equal to x naught plus t times v1, y equal to y naught plus t times v2. So here is a parametric equation created from given point and a parallel vector to the line here. Now, in this parametric equation, I chose parameter t, and it's really up to you to choose any parameters you want. Okay, so mathematically, you can use any parameter or variable at here for this parameter. Okay, so t here is just called parameter. Okay, so mathematically, it's just a parameter. It's a variable. You plug in, so x naught, v1 are the given quantity, and you plug in different numbers for the t or the parameter, then you get a different value for the x, y, z, and that's the coordinates. That's the coordinates for any point on the line at here, right? Okay. So bear in mind of the physical meanings of this. So here is L, here is V, here is a certain point P naught, and then you have any other point P at here, right? So that P at here is x, y, z, which is described by these 3 equations at here. So that's pure mathematical meaning. Now I'll give you an example actually to give it a little more specific meaning here. Essentially, we can think about it as a trajectory, a point that is traveling along, right? But in essence, this is a line equation. Now from here, as I typically will emphasize, this is one direction, right? For a certain question. What's the line equation? So then you need a point and you need a vector that is parallel to the line so that you can create this line equation. As you can see here, this is basically your point P naught, and here is your parallel vector V at here, right? That's how you can construct line equation. A line equation is not, parametric equation for line is not unique, because you can choose any other known points on the line. So you can change this x naught, y naught, z naught to different values as long as it's along the line. But once they change it, then the parametric equation is different. And you can also scale this parallel vector v1, v2, v3 to any multiples. Then this vector changes, and this parametric equation also changes. So that essentially gives you infinite number of solutions or parametric equations for the same line at here. Right? So that's what I meant in the previous lecture. So there are infinite number of parametric equation for the same line. Okay. So just bear in mind of this at here. Okay. Now before we move on to the to an examples here, there is actually a different way of writing this one. So here I wrote down 1, 2, 3, basically 3 expressions set here, right, representing this line equation. You can also write down this 3 equations to be like the following in here. So define, let's say, we define a position vector. Okay, define a position vector R naught, X naught, Y naught, Z naught. Okay, so here is basically what I mean in here. And I'll draw the line again. Okay, so here's line L, and here's your P naught at here, and this is your arbitrary point P at here. P naught is R naught, X naught, Y naught, Z naught coordinates. So we can create a position vector. Okay, position vector basically means you create a vector between the origin and the existing location. So this is your position vector R naught. And then you can create another position vector at here, which is representing the position P. And let's call it R vector. Right, so there are 2 position vectors at here. Okay. And now, if I go back to the parametric equation that written down at here, so then you can literally see you have, this is your position vector, this is a parallel vector, and this is the position vector for the capital P, right? So you can write down that 3 equation in a much brief and short form, which is R equal to R naught plus T times V. Okay, can you see that? Right? So you put R at here, right? So on one side R is X, Y, Z, and this side R naught, X naught, Y naught, Z naught, and then T, V1, V2, V3. I'm kind of using column vector here now, but that's the gist of it, basically. Okay. So for parametric equation, you could use this, okay, instead of this. But in most of my lecture notes and assignments, tutorial notes, I think most of the time I breaking down into 3 expressions for line equations. Okay, yeah. But just bear in mind, you know, you can also write it like this. Any questions so far? Okay, yeah. So as I mentioned, here the T here is just a parameter. I also want to emphasize this here. You can choose to use any other symbols or parameters. Okay. But once you change the symbol, this is also mathematical. If you change from T to something else, then the X, Y, Z here, okay, you know, mathematically, here I say X is a function of T, Y is a function of T, Z is a function of T. If I change these to different symbols, then I will say X is a function of S, Y is a function of S, Z is a function of S. So you just call it different, right? Yeah. Okay, so let's continue in here. Let's look at examples now. Okay. Yeah. I think some of you have already jumped ahead of the assignments, so you have pretty good idea of what are the examples related to lines. So I'm going to jump into the typical, my favorite type of question, for calculating distance, which is one type of question that we are giving to you in the assignments. So giving you a point S, here is coordinates for the S, and also given a line L with a parametric equation So given these two information, and we wanted to calculate what is the shortest distance from this point S to the line L. And in previous lecture we had an example given a point S and a plane, and what's the shorter distance from that point S to the plane. So that's, as I said, that's my favorite kind of question. And I'm actually really glad, when I put down this question in the first lecture, and a couple of you guys were so excited, actually immediately jump onto it. May not be able to finish the calculation, but there are a couple of you actually showed me their procedures of how to proceed, how to solve this question. And one of them showed a question which is actually a solution that I never thought of. And the other day there was another student came to the office and showed me another approach, which is also an approach I never thought of. So that's very exciting, right? As a matter of fact, before these two students came to me, I already had like 4 or 5 solutions. And now plus these two, I think I probably now have 6 different kind of solutions now. So I'll give you this kind of all different kind of possibilities in the lecture notes, okay? But in respect, what kind of approach you wanted to do, right? But let's set the target, let's set a goal right, in order to solve this question. Because you're looking for is the shorter distance d here. Then, there are different ways of thought. As I mentioned, this is not a high school geometry question. This is a type of question I expect you to use vector concept. Basically means dot product or cross product, right? That kind of concept. So then, given this, right, before we start to solve for anything else, as we did for the plane equations, because you're given a point S, you're given a line equation here. The first step what you do, okay, so always the first step, if you're given any questions, for any question before you start solving, write down the known information based on the given one. So for example, here's the line equation here, right? Let's write down what is the parallel vector. So let's write down the parallel vector V, okay, based on the given question. So here's L. So all you need to do is parallel vector, as I mentioned in the line equation, that's the coefficient for the parameter t, right? Parameter t. Then I look at the coefficient for the parameter t and extract it out as my parallel vector. And I look at the coefficient, it's 1, -1, 2. So that's the first step you need to do. Okay, and you can always draw an illustration in here to just basically tell you what this vector actually means to you, right? Now, a common mistake, okay, I've seen in the past, when people write down the coefficients, a very common mistake is you look at this one here, right? It's supposed to be -1, but a lot of students just write down 1. Okay, and that's a very dire mistake to make at this first step, because you have this negative sign neglected, and the rest all of the calculations will be wrong. Okay? So make sure the coefficient here, right? If you look at the coefficient here, that's when you put a positive, and the rest of the number is the coefficient. Okay. All right, and then the second information, right, you can write down based on the given line equation is what's a given point that the line goes through. Okay, there are infinite number of points, right? There are infinite number of points here, but you can always write down the most obvious point. And there are infinite number. The most obvious point is this constants at here listed in the line equation. So I'll call it P naught, or just call it P. and then that equal to 1, 3, 2. And we don't know exactly where it is, but you can always basically write down this point P. Yes? 130, exactly. Thank you. Okay. And that's another common mistake people make. It's like the mistake I'm making, right? Yeah. So we always double check these numbers. Good. Once you put these things down, now you can think about which tool I can use, right, to derive for this shorter distance d. Okay. One of the common methods that I think I reviewed, right, and I emphasized a couple of times. Okay, when you try to find a distance or a length, okay, one of the things that we have mentioned is you can use a vector and then dot. What other type of vector? A vector dot a unit vector, right? So when you use a vector dot a unit vector, then you get the projected length. Okay, that's a very useful tool to make use of. Okay. So here is the length we're looking for it here. I guess if I want to use that type of thinking, then I have to find a vector and then project into that direction in order to get this shorter distance d. That makes sense? Right? That's one thinking I can make use of that concept. Right? Good. So let's think about that approach for now, and then I'll give you a couple more examples. Now, if I want to do that, then I guess I need what? I need to know what is that direction. Okay, so I don't have the direction, right? I don't have the direction for this one here. Okay, so right now I didn't write a unit vector. I'll just write a vector in that direction, which is fine. So if I can find a vector in that direction, I can just normalize it and it become a unit vector. Okay. But the point is, as we just discussed, maybe I really want to find this direction pointing to the point P. Okay. Second of all, I need a vector. I need a vector so I can project the vector onto that direction. Now this actually seems to be obvious because I have an S at here, I have a P at here. So I could simply create a vector, PS, okay, and that I can project the PS into the direction N over there. That makes sense? Okay, yeah. So that's a very unnatural thinking in here actually, okay? Yeah. Okay, so how do I find this N direction then, right? If it is not given, okay, if it is not given at here, should I directly find this N, or can I indirectly maybe find the N at here? Okay, so that's the point. So let's look at the first, maybe look at the first methods at here. Okay, let's look at the first method. And I'll present this method. Actually, this is one of the student method here. So I'll present his approach. Honestly, I didn't put it in my lecture notes, so I may not be able to write down all the detailed calculation. But I'll give you the steps of this approach at here. Okay? Yeah. I think it's Isaac, right? Isaac, you give me this approach here. Anyway, so let's think about this N here. Okay, so you need a little bit 3D visualization in here. So here's what I would do. I'll show you here. First of all, you have a PS here, and you have the V vector here. Okay, so I will do a PS, create the PS vector, and then I will cross this V vector. Okay. So here's a PS, here's a V. So if you do the cross product, guess where is that vector? So you can put this V at here, okay, as close as possible. Okay. When you do a cross product, use the right hand rule, right? Literally, it should go into the page, right? Go into the page. If you use a V cross PS, then it goes out the page. That make sense, right? So that's a vector you will get out of the PS cross V. You can call it any tempered vectors you want. Okay, let's I don't know, let's call it maybe n1. Okay, let's call it temporary vector, call it v1. Okay, so you have PS, V, and PS at here, and so it's hard to visualize, but you got n at here. Okay. You know, I'll just write down V cross PS to make my drawing a little bit easier. Okay, so that's a vector you get, okay, perpendicular to the V vector and also the PS vector. Okay, that's a cross product. And P is given, S is given, and V is given. So you can use cross product to calculate. Okay. Since I don't have the, I didn't do the calculation, so I want you to do your calculation, but I'll give you some other approach which I did a calculation myself. But PS, so let's write down the PS first. Okay, PS is the coordinate of S minus the coordinates of P. Okay. So S is 115, P is 130. Okay. 1 minus 1. 1 minus 3, 5 minus 0, which is 0, negative 2, 5. Okay, that's your PS vector. Okay, and then you do the cross product, which is to calculate the determinant of the 3 by 3 matrix. So you write down the matrix 1, negative 1, 2, 0, negative 2, 5. Okay. So now you can calculate this cross product. Okay. So try it out. Okay. Is that good? So far so good? So now if you come back to this drawing in here, right? So if I use V cross PS, so I got a vector perpendicular to the plane, right? To which plane? To the plane containing this whole chunk of lines and points. Good? And then next step, remember the objective is to get a vector pointing this way, right? Pointing this way. And then now you get a vector perpendicular to the plane, which is also perpendicular basically to the V at here, right? To the V at here. Now next step, if I can use N here, this N1, and then cross the V. Okay. So I wanted to find a better, will be a better drawing here. So can you visualize that? So if you have a vector N pointing out of the plane, and then you have a parallel vector V, right, which is also, of course, perpendicular to the N that you just calculated. And then you do another cross product between this N1 and the V. And guess what that direction of the results cross product pointing to? Which is what? Exactly the direction we're looking for, right? So this basically will give us that N vector over there. And that's actually a pretty good approach in here. So two cross product will give you this normal vector, this N vector here, which is perpendicular to the L. So I wish I have a better way of illustrating. So let me try it again in here. Okay, so it's not complete in flat in the drawing. You can probably visualize this is in a plane like that. So two cross product. First product, create this N1, and then second cross product, create this N and here. And that N is the normal direction to the line L. Okay, so you could do another cross product based on the results of N1, and then get this N, and now you can normalize the N to obtain a unit vector, and then you get your D, which is basically your PS dot N hat. So that's the first approach. I didn't give you all the detailed calculation. You can try yourself, and I'll give you another one which I'll give you a detailed calculation. Does that make sense? Yeah. I think the only challenge here probably sometimes is trying to visualize all these, perpendicular vectors after the cross product. Okay. Any questions so far? All good? Okay. No hands means good. Okay. Okay. Let me show you another method then. Show you another one. Now in this one here, the objective, okay, is not to find this N vector. Okay? It's not to find this N vector here. So let me redraw the illustration at here. So the objective is sort of the idea of this right angle triangle at here. Okay. If I cannot get this D strict directly, the question here is maybe can I get the projected length of this part first, and then get this part next. Right, that's another way of thinking. Well, as a matter of fact, we did similar examples in a lecture. Basically, you can always decompose, right? You can always decompose a vector into two vectors, two perpendicular ones. So that's exactly what happens right here. If I can decompose the PS into this one and this one, which we call the parallel vector and the perpendicular vector, then if I can get the parallel vector first, then I can subtract to get a perpendicular, then I get the length of the perpendicular, which is the D. So that's the second. That's another method here I would use try it out. So the project vector in the V, and that's actually quite easy to obtain because we did that in the lecture here. So this is called PS parallel, and this portion in here is called PS perpendicular. That's the projection. That's decomposition of a vector. So let's take a look at the PS parallel first. And this is more or less should become a formula now. So when you're looking for a projected vector in a certain direction, there are always two components. One is direction, which is this direction, and that's your V hat. Another is the length of the projection. Length of projection means you use the PS dot the unit vector of that direction, which is the V hat again. So together you get your PS parallel. Right. So in the class we use a symbol. This is basically this essentially we call that projection of PS in the V hat direction. That's the projected vector. which is PS parallel. The calculation should be straightforward because you have all the given informations, and V hat is V over the magnitude of V, and PS we have calculated. Okay, so I can extract all the information out. Okay. You can calculate what V over V. So V is what? 1, negative 1, 2. Then, so let me write down it separately. Okay. So 1, negative 1, 2. So the bottom here is 1 plus 1 plus 4. And then top here 1, negative 1, 2. So 1 plus 1 is 2 plus 4 is 6. So that's 1 over root 6. And then 1, negative 1, 2. Okay, that's your V hat. Okay, that's your V hat. PS we have already calculated. So let me write down it here again. And the rest of things are just straightforward calculation now. You calculate dot product. So calculate this guy dot the V hat. So let's try it out. So PS dot V hat equal to what? Equal this times this plus this times this plus this times this, which is 1 over root 2. There's a common factor right here. 0 plus 2 plus 10. So give us 12, right? Okay, give us a 12. That's dot product. That's the length of the projection, right? The length of the projection. From here, sometimes students actually rely on the Pythagorean theorem, but let's use a vector here. Okay? Then I can calculate PS parallel, which is PS dot V hat, and then times V hat. 12 over root 6 times V hat is 1 over root 6 again. And then 1, negative 1, 2. Root 6 times root 6 is 6. Then 12 divided by 6, 2. So 2 times 1, negative 1, 2. Which is 2, negative 2, 4. That's your PS parallel. Once you get the PS parallel, then you go back to this, basically the drawing and here. Here you have a triangle at here with the 3 sides, having 3 sides of the 3 vectors at here with the directions pointing as illustrated like this. So PS perpendicular is basically PS minus PS parallel, and that gives us the PS perpendicular. PS is already here, PS parallel is here, so this minus 2, negative 2, that minus that, which is 0, 5 minus that is 1, so it's negative 2, 0, 1, and then finally your distance is the norm of this PS perpendicular, give us a root 5. Okay. Okay, that's another approach. Any questions regarding this approach right here? Good. All right. So let's take a look at another approach here. Okay. I really wanted to present all the different approaches, actually, just to let you see all the possible, applications, right, of what we learned, the simple concept, vector concept here. Now, in this one here, this approach here, we actually make use of a cross product again. Okay. All right. So let me draw this again. So here is PS. And here is the line L. Okay? And then you have a vector V over here. Good. Okay, so I'm going to write down this first, and then actually I'll explain. Actually, you will see where it comes from. Okay. I'll directly jump into the calculation of PS cross V. Okay, I'll directly jump into it because I have PS and I have V at here, and I know what PS cross V the formula is, because this is the length. So when I do the calculation, the formula basically says for the length of this cross product, it's the norm of V and the norm of PS, and then times the sine theta, right? Theta is the angle between the two vectors. Just write it down, this formula here. Really, for right now, it really doesn't mean anything, right? But it's a formula based on the given condition. But however, if I examine it a little closer, right? If I examine this a little closer here, and particularly if I look at what PS, this length PS times sine theta. So here's the PS, here's the theta. And look, what is PS times sine theta? So if I create a right triangle here, and PS, which is the length, this is the length of PS here. That's the hypotenuse, right? And then when you use that length times sine theta, guess what do we get? We get this opposite side, the D, which is the shorter distance D, isn't it? Right? So this guy here essentially is the D we're looking for. Okay. So that's simple formula. At the beginning we don't know what it is, but then examine here. Look, here's the D we're looking for, right? And what's even better is you really have all of this information already. So then my D really just equal to what? Equal to this division at here, the fraction of that cross product, and then over the norm of the parallel vector V. So these things, this is quite actually save a lot of the computation compared to the other two methods. Okay. So literally you're just doing one calculation in here, and then let's do a calculation, because I do have the cross product for this one in here. Okay, this norm here, the determinant. Okay, the determinant. So your result of this 3 by 3 matrix determinant is I hat plus 5J hat plus 2K hat. I always encourage you to do hand calculations. Okay, always try hand calculations for now, and use MATLAB or any other calculators to help you to verify at this stage, because you don't have the luxury of a calculator in the exam. And I actually, when I talk to high school teachers nowadays, all of them emphasizes strengthening the computation skill. Because I know my daughters, they heavily rely on calculators nowadays, even for very simple calculations. You know, sometimes as simple as, so what's 1/4 equal to, right? So that kind of a calculation, that's not good. So emphasize the hand calculation. So if you get this one here, and then the V, we got it. So D basically equal to the length of this 1 plus 25 plus 4. And then divided by root 6, we'll get the same answer as the previous one. This is root 5. Is that clear? Right? Okay. Okay, so I think I wanted to dig this method a little bit deeper. Actually, I want to relate. Now you'll see it really relates to one of the example we did in the previous lecture here. Okay, so let me do this. Here is my PS vector. Here is the V vector here. Okay, here's a V vector, and that's what we're using, right, in this example here. Okay, so now I'm gonna create a parallelogram. Okay, here's the parallelogram I created. Can anybody tell me what is the area of this parallelogram? PS cross V. Excellent. So that's what we learned. That's what we learned in the previous lecture. That's the area of the parallelogram. If I resort back to the basic formula for calculating a parallelogram, the same area will also equal to the base length times what? Times the height. Right? That's how we start calculating the formula. And in this particular case, what's the height? It's the D. And what is the base length? That's the V here. And now you can see what is the shorter distance or the height D, which is what? That's this, right? That's this. Okay. So basically this formula here pretty much is the height equal to the area divided by the base length. Right? So that completely give a different meaning now, right? Rather than just a cross product. Is that clear? Yeah. So that's another approach right here. Okay, that's an approach. There is one more approach right here which I wanted to give to you, but without doing the calculation though. Without doing the calculation. Okay. Now in this particular approach, the idea is, okay, it's more or less like solving a typical geometry question. So if I project S to the line L and perpendicular, of course, then naturally, there should be a point at here, right? Let's call it Q point. Okay. So if I can find the coordinates for the point Q, and then I can find what the distance between Q and S. That makes sense, right? And that's a very natural thinking too. Yeah. But of course, we just don't have the Q for now, right? And so this is approach right here is to find this Q point such that this QS is perpendicular to the L. Okay. Or find the Q point on line L such that the QS is perpendicular to the L. Okay. That's this way of thinking it here. So how do I find this point Q then, right? Yeah. As a matter of fact, in the lecture you will see two different ways of finding point Q, and then I'll give you one in here, which is one of the students actually showed me the other day. So I'm going to draw this just slightly just to have a better illustration though, okay? So let's draw it to just slightly different way of here. So I'm gonna I'm going to draw a line L, okay, passing through a plane at here, okay? And here's point P, here is point S. So you'll see the plane I'm drawing here is not an arbitrary plane. So I draw the plane at here, the passing through this point S. At the same time, this plane is also perpendicular to the L. So here's the special plane I just drew it here. So this plane is perpendicular to the L and passing through S. Given these two conditions, you actually have a unique plane in here. So basically create a plane passing through S and perpendicular to line L. Okay, that's how this plane is created here. Because why do we do this? Because you look at this one here. If I create this plane and the perpendicular to the L and passing through the S, guess what will be the intersection point between this L and the plane? That's exactly what the Q point we're looking for here, right? That's exactly the Q point we're looking for. That make sense? Okay. So now boils down to finding the intersection between the plane and the line L. And then you'll find the Q point. But of course, the first step, we have to find what is the plane equation first, right? And that actually is pretty straightforward, because to create a plane equation, what information do you need? Not a parallel vector, perpendicular, right? A normal vector to the plane and the point S. Good? So you already have a point S. That's where the plane is passing through. Then what would be the normal vector then to the plane? What would that be? V, exactly, right? Because plane is parallel to the L and the plane is perpendicular to the V. Then all I need is to create the plane by substituting into the plane equation. Okay, which is this one. Okay? And ABCs are the normal vector. X naught, Y naught, Z naught is the point the plane goes through. And V at here happen to be 1. So X minus point S, and B is -1, Y minus 1, and C is 2, and Z minus 5. That's your plane equation. Let's simplify this a little bit. You get X plus, that's not plus, X minus Y, okay, plus 2Z, and what are the constants at here? So 1 plus -1 is -1. -1 plus negative multiplied by -1 is +1, so that actually cancel. And then you have a 2 multiplied by -10, and move it to the other side, you got a +10. So I simplify to this simple one here for the plane equation. Is that clear? Okay. And then that's the question, the next one. What's the intersection? How do I obtain an intersection between the line L and the plane of this one here? So how do I do next? So I have my line L, right? This is given here. This is your line L at here. Okay, this is your line L. Okay. How do I get the intersection between this line L and the plane? What will be the approach? Anybody? Yes?
Insert the equations for line L into the plane equation.
Exactly. Right. That's how you normally solve for intersection, right? You substitute one into the other. Okay. In this particular case, you sub the line L equation into the above one, okay, into this plane equation. And line L has, so x replaced with 1 plus t, and y replaced with 3 minus t, and z replaced with 2t. Okay. One equation, one variable t. So you can solve for t now, and t end up to be 2, I believe. Once you get the t, then you substitute the t back into this line equation, which will give you the coordinates for the q. So the coordinates for the q equal to 1 plus 2 and 3 minus 2 and 2 times 2. So 3, 1, 4. Finally, create this QS vector, and then calculate norm, get a shorter distance. Yes?
How do you know that QS is a
Yeah, that's a very good point. Because what? Because right, because the plane we created here, right, is perpendicular to the line L, which means the line L is perpendicular to the plane. Okay. It's redundant, right?
But then the point Q could be anywhere.
Sorry, come again?
The point Q could be any intersection between the plane and the line.
Not any, because when you have one single line perpendicular to the plane, you only create one single Q point, intersection point.
How do you look at the Q and the S are
Well, see, if this line is perpendicular to the plane, guess what? This line must be perpendicular to any lines or any vectors on that plane. Can you imagine that? Right? If you have a line perpendicular to this table here, for any straight line, right, any vectors on this plane, that line is perpendicular to it. Basically means the QS here is perpendicular to this line L. Good question. Yeah. So good? So I think there are a couple more different methods in my lecture notes, which you will see. May not be as straightforward as easy as this, but they all still give you a different perspective. Okay? Yeah. So I encourage you to try out all of this. I think this is really good actually to expand your visions in terms of using all the simple concept here, right? All the different roads leads to Rome, basically. Okay. All right. So another type of question, okay, which I won't be able to have the time to solve it here, but I want you to think about it, okay, on your own. Okay. You don't have to have a specific number, but just think about the approach that you can use to solve. Okay. So here's another typical kind of question here. Not necessarily this is related to line now. Okay, so we're now oftentimes mixing lines and planes together. So if I have two planes, plane 1 and plane 2, and these two planes are parallel to each other. Okay, so parallel planes. Can you find the shorter distance between the two planes? So given the two planes, okay, think about it. These two planes are given. Okay. That's another type of a distance question. Okay, and then there's another one in here, another type. Given two lines. Okay, so here's line 1, here's line 2. Okay, so when you have two lines, now these two lines, okay, in this case, I call it skewered. Okay, I call it skewered. So I think I mentioned in the previous lecture, when you have two lines in 3D space, what are the geometric relationship? So they could be parallel, right? They could be exactly the same. They could also be what? Intersect. Then they could also be like this, right? Not parallel, nor intersecting, and this is what we call skewered. Okay, skewered two lines. So if these two are skewed at here, if they're two skewed lines at here, then how can I find the shortest distance, okay, between the two lines? So you can imagine if you have two lines here, this means a shorter distance, not a distance basically connecting any 2 points on the two lines, right? Basically means you need a line between this L1, L2, and this line is actually perpendicular to both line L1 and L2. And how do I get this distance D? They are seemingly actually different questions, like this and this, but really they're still kind of question looking for distance. So all the different kind of thinking that we just gone through applies exactly to this kind of question. Okay, so I want you to think about it. Okay, for the type of question like this, what will be your approach? You can even just literally give yourself some lines, right, and then to do some calculations if you want. So that's another two questions I want you to think about, okay? And feel free to come to my office to ask me if you want. Any questions so far? All good? All right. So let's look at one more example here. Okay? Then, hopefully I can do a little summary. Okay. So for this example here, it's a very interesting example. Okay. I'll write down example first. So I'll give you a cat traveling along a straight line trajectory. So here's a trajectory for a cat. And here's a trajectory for a mouse. Given two trajectories. Now this time, okay, I'm gonna give it a very specific meaning now, okay, to the trajectory. It's not just a mathematical parametric equation. I will call this is the motion. Okay, this is the trajectory the cat is traveling. This trajectory the mouse is traveling. So like a Tom and Jerry area here. So now the question is, okay, will the cat catch the mouse? So this is not exactly the kind of solving just a parametric equation. This is more of a physical type of phenomenon. Okay, yeah. Will the cat catch the mouse if this is the motion of the cat, if this is the motion of the mouse? So first step, what we had to translate is what type of motion are we talking about for the cat? What type of motion are we talking about for the mouse? Right. So if I come back to the cat here, apparently I'll see, okay, so this is a time history function, this is a time history trajectory. So apparently at t equal to 0, at the time equal to 0 moment, where is the cat? Right? The cat is at which point? -4, 7. That's the coordinates of the cat, which is, let's call it initial location, right, for a certain motion. And then the mouse is at 1, -6. And how does the cat travel out of here? So, and this is actually back to the beginning, how we derived a line equation, right? If you recall that. The coefficient for the t at here, mathematically it means it's a parallel vector, right? It's a parallel vector here. But when we derive this coefficient here has another meaning, which is what? If you recall that, the parallel vector, this coefficients here, this also means velocity, right? So the cat is also traveling at a constant velocity, which is the coefficient, and that's 2, -3. Oh, that's right. Let's call this. This is v1. So 2, -3. I'll put everything in 3D perspective. So I'll put a 0 out of here. Put everything just still in the 3D perspective. Okay. And the mouse is also traveling at a constant velocity, and that's 1, 4, 0. So now things becoming pretty kind of straightforward now. So your thinking is basically, so the cat starts here, the mouse starts there, and the cat is traveling this constant velocity, the mouse is traveling at this much constant velocity, right? And the question is, will the cat catch the mouse? Okay. And I think I'm going to put a 0 here just to put it as a 3D coordinates. Okay. So I have a drawing at here just to help with the understanding at here. So what do we mean by catch, right? So if I draw the line out, first of all, the line given at here, or the trajectory given at here, the trajectory given here, they're just x and y. So basically they're all in the xy plane, right? And when you draw two lines in xy plane, they definitely will intersect. So when you draw the trajectory out, they definitely intersect. So that's basically what this looks like. When you draw the two trajectory, they definitely intersect. There's certain intersection points. But that's just mathematical meaning, right? Intersection. But here we're talking about the catch. Basically means there's a particle moving on this line, which is the cat. There's another particle moving on this line, which is the mouse. And when we're talking about the catch, it really means what? The cat and the mouse has to end up at this intersection point exactly at the same time, right? So that's what we mean by the catch at here. Okay, yeah. So it doesn't mean the intersection. The catch doesn't mean intersection here. Okay, but intersection do actually is a useful information in this particular case. Okay? So that's the point. In order to prove whether it can catch or not, okay, so the other way I think I also want you to understand a little better about the parametric equation again is, you look at the way I wrote the parametric equation. Right now, the two parametric equations all written in parameter t, right? They're all in parameter t, which has the same meaning, which is the time. So when you change the time at the same time, when you have a time change from 1 second, 0 second to 1 second to 2 seconds, and the coordinates of the cat, the coordinates of the mouse will change accordingly, right? At the same time. So basically means, can I find a value of a t, right? Can I find a value of a t such that the coordinates of cat will be the same as the coordinates of the mouse? That basically is what we're talking about, the catch, right? So you all start at t equal to 0. Apparently they're on the same location. Okay? As t changes, is there a certain value of the t such that the xy value for the cat will be the same as xy value for the mouse? That's the catch. Okay, that's what I mean by catch. So that thing's actually becoming a little easier now. So basically means I want to find a t such that this x is the same as this x and this y is the same as this y. So what do we do now? I can let this x to be this x, right? Because I'm really trying to find it out. Let's force this x to be this x. And that's fine. So if you do that, what's the solution for the t? In this case, 2t minus t is t, negative 4 move to the other side, you get a t equal to 5, right? You get a t equal to 5. Okay? So when t equal to 5, these two x's, right, the two x components are the same. But does it mean that when t equal to 5, the two y coordinates will be the same? So what do? We substitute the t back into this y, back into this y. And we verify, right? We verify here. So at t equal to 5, and we get the y cat equal to, what's the value? 7 minus 15, which is negative 8. And then the y mouse is negative 6 plus 20, which is 14. That's way off, right? Yeah, that's way off. So at that particular time, your t equal to 5 satisfy the x, but doesn't satisfy y. Okay, which basically means, will the cat catch the mouse? No, right? Yeah. So there's no way the cat will catch the mouse, or there's no way that the cat will meet the mouse at the intersection point. Okay? Yeah. Alright, good. So that answers the question now, but it does beg the question, what bothers me now, then how do I make the cat, how do I make Tom to be able to catch the carry? In the animation, Tom never catches carries, right? How do I make sure that the cat can catch the mouse? What do I have to do? Oh, now what do I have to do? What does Tom have to do in order to catch the mouse? Okay? Yeah. So you go back to the equation here. What can the cat do in order to catch the mouse? Here is the equation here, right? Let's see, it does have the flexibility to do some sort of some kind of flexibility for changing here. What could you do to change? You can change what? You can change its initial location, right? You could also change what? Its velocity. So maybe it's too slow, or maybe it's too fast, right? Who knows? But maybe we can change its velocity, or maybe we can change the initial position. Okay? You can change both, or you can just change one. Okay, just to try it out. So let's basically look at this this answer here, right? So suppose we change the velocity for the cat. Okay, suppose we change the velocity of the cat. To what new velocity for the cat such that it will be able to catch the mouse thing, right? That's the point here. So let's think about it, okay? So changing the velocity basically means, what's the current velocity? So current velocity is v1 equal to 2, negative 3, 0. Okay, so that's the current velocity. Okay. Changing to a different velocity essentially means you're not changing direction, right? You're still constant velocity. So basically means your new velocity is essentially what? What's the difference between the new velocity and this current velocity? It's just the difference of scale, right? It's just a scale difference. So I might as well do this. I'm going to normalize this v1 to a unit vector, okay? And so 4 plus 9 is root 13. So that's a unit vector. Then the new velocity, so let's call it v new. It's basically just a scale difference, so I'll use a c times v1 hat. Okay. It's going to be a multiple of this unit vector, which turned out to be c times root 13 to negative 3, 0. Okay, that's the new velocity. I just don't know what the c is yet, but I want to find a proper value for the c so that the cat can catch the mouse. Good. Given the new velocity, basically means the cat will have a slight different parametric equation now, right? Then that's a c times 1 over root 13, and then there's 2 at here too, times t, and y times 7 plus c times negative 3 over root 13 times this. So let's just put a minus here. Okay, so this is a new parametric equation. Well, that's the new motion, right? It's a new updated motion for the cat. Okay. Okay. Yeah. Okay. So the bottom line is, catch basically means the cat has to end up at this location here, right? The cat has to end up at this location, because if end up anywhere location, it won't catch the mouse. The cat has to meet the mouse at this location at here. Okay. So let's do this first now, right? You have line 1L, which is x equal to negative 4 plus 2t originally. But now I wanted to do this step here. I want to calculate what is that intersection point, because when we talk about the cat has to end up at that location, right? Has to end up at the intersection location, irrespective of what. Okay, so you have a new velocity, you have a old velocity, so really you want to end up at that particular location at the same time as a mouse. So I want to know the location now, right? I need to know the location. So I need to calculate basically. I'll write down the one sentence at here, okay, before I write down the equation. What is the intersection point? Okay, what is the intersection point? So when we talk about the intersection point now, an intersection between the two lines, we have to change our understanding of the parametric equation slightly. So originally your L1, right, equation is written as x equal to negative 4 plus 2t, right? And the y equal to 7 minus 3t. And L2 is written as x equal to 1 plus t and y equal to negative 6 plus 4t. Okay. But if I want to find intersection between two curves or two lines, I cannot use the same t as a parameter anymore. Okay, I cannot use it anymore. Because when I use the same t at here, remember what that physical meaning is what? A trajectory. And then the t changes, all the points change at the same time, right? But when you try to find intersection between two lines, you can't use the same t anymore. So you have to change this to a different parameter that's called s at here. You can still keep the t at here. You can even change the t to a different parameter that's called a k. It really doesn't matter. Okay? So that basically the meaning, getting back to a simple mathematical meaning now. Two line equations, two parametric equations, what's the intersection point? They have to be different parameters in order to solve for intersection point. Okay? So here is basically two different set of equation now. Okay? One x of function s, y is function s, x is function k, y is function k. Intersection basically means solving for this set of equations, right? When s equals to a certain value, this line equation end up this point. When k equals to a certain value, the blue line end up this point. That's how you can solve for intersection points. Right, so s equal to something leads to point P, and k equal to something leads to the point P. Let's say that's the point P is the intersection point. Let's call it. Okay, that's the idea. Okay, so then how do I solve for this then? This is your typical approach to solve for intersection. Okay, for two lines. If it's a 3D, that still doesn't matter because this is 2D. I only have two equations. So how you do is you let this function x to be this function x. So that's negative 4 plus 2s equal to 1 plus k. And then let the y equal to this. And that's how you solve for intersections. You have two equations, two unknowns, and you will be able to solve for the answer here. S equal to 3, and then k equal to 1. Okay, k equal to 1. That's intersection. So then you can substitute s and k back into this equation. You'll be able to find what's the p coordinates. So if I substitute, let's say use a k here, 1 here, you have 2 at here, 1 here, negative 2 at here. So that's your intersection point. 2, negative 2. If you substitute s back into this equation, you'll get exactly the same point. Is that good? Okay. So, sorry, I'm a little bit falling behind in here. Let me finish this question at the beginning of the next lecture. Okay? Yeah. But otherwise, you're all ready for the second assignments. Okay? Any questions so far? It's all good? Okay. Hi. Yeah.
About the square on the top. So why do you divide it by 3?
Let me maybe first. Sorry. Let me.
I mean, can we combine these to